one number. Okay, speak up. The normalized wave function in the momentum space of a particle in one dimension, that is pi of p. Okay, what is that in the position space? In the position space, have you note down this one? Momentum space. I mean, position space means you are going to use psi. Okay, x or x comma t. Momentum space you are going to use pi of p, isn't it? So I'll just write psi of x here. Okay, speak up. So then in the position space, your x cap is equal to x itself. Okay, p cap is equal to minus I h bar dou by dou x. Okay, whatever the, I mean, position space means, I mean, whatever the state is represented by position space wave function. The same state can be represented by momentum space wave function also. It has equal strength actually. Okay, speak up. So like that it will continue. Am I right? If you want to find expectation x here, there are two ways. One is x into mod psi square dx. Why? Because this mod psi square is position probability. Am I right? Or what you can do, you can sandwich x cap between psi star and psi. But while finding expectation p, you have to sandwich it. Am I right? There are no other option. Psi star p cap psi dx. Am I right? Speak up. Where p cap is minus I h bar dou by dou x. Okay, there are no other choice. I think I mentioned in the problem. Okay, speak up. Check this out. Okay, but in the momentum space, okay, speak up. This p cap operator is p itself, because this is the momentum probability distribution. Am I right? This will give you momentum probability distribution. Expectation p, you can write p into mod phi of p whole square dp directly, isn't it? But if you want to find position, what you call x cap related, what is x cap here? I think plus I h bar. Anyone? Dou by dou p plus I h bar. Sure. So while finding expectation x, I mean this would be wrong. X into mod phi of p the whole square dxy, because this is a momentum probability. Okay, this cannot be done like this. Am I right? Speak up. So that's why what you have to do, you have to sandwich. Speak up. Phi star phi of p the star. What is this? I h bar dou by dou p. Okay, phi of p dp. He mentioned in the problem. I hope I have asked you to note down that one. Okay, speak up. Position space, momentum space. Now look at here. Some what you call calculations will be easy in position space. Some calculations will be easy in momentum space. Are you getting my point? Now whatever the question he's asking, look at here. So phi of p, am I right? That's equal to, I mean that alpha, I'll write it as normalization constant a. Okay. Remember this functionality does matter. Okay, 1 by what you have, p square plus beta square. This is the functionality part. Okay, so alpha will be somehow function of beta only. Am I right? When you normalize this one. Okay, speak up. I'll keep that normalization constant as a. Okay, speak up. So now then if he asks uncertainty in sigma x or delta x, whatever, okay, what you have to do, you have to find root of expectation x square minus expectation x the whole square. But expectation x in momentum space is lengthy. One thing is you need to normalize this one first. Okay, that integral you should know. Am I right? P square plus beta square whole raised to 4. I mean, you have to do tan theta substitution and you have to do that integral. Okay. So other one is, okay, expectation x in momentum space is difficult. Am I right? You have to sandwich that operator, isn't it? Then you have to do. And expectation x square. Expectation x, I can say it is 0. Am I right? In the momentum space, how? I will remain. Okay. If that integral is non-zero, I will remain. Isn't it? The same idea. Okay. But what if expectation x square comes? That's equal to, look at here, pi star of p. Okay, what is this one? Minus h bar square dou square by dou p square. Okay, pi of p dp. So now this expectation x in the momentum space is quite difficult. Okay, then what you can do? You Fourier transform, find position space wave function. Is that okay? Speak up. What is your position space wave function? 1 by root of 2 pi h bar. Okay, integral minus into plus infinity. What is that? A by p square plus beta square e power I. I'll write x by h bar into p into dp. integral with respect to p, isn't it? Now this integral should be known. What is this one? 1 by root of a by root of 2 pi h bar. Okay, so integral minus infinity to plus infinity. Okay, e power I x by h bar into p divided by p square plus beta square into dp. I gave this integral. I gave like this integral minus infinity to plus infinity e power I kx into I think x square plus a square. I gave like this dx here. Okay, speak up. What is this one? Pi by a. Okay, e power minus a mod k. Is that right? A mod k. Now you need to think quite reverse over there. Okay, speak up. So what I have here minus infinity to plus infinity e power I. Okay, in place of k I have x by h bar into p here. In place of x you have p square plus beta square dp. Am I right? Can you see? So that's why it is pi by beta. Okay, pick up e power minus beta mod x by h bar. Am I right? X by h bar. What do you say? Now look into this one. Okay, so what I do is, okay, all of these constants, okay, all of those multiplicative constants, I don't worry. Okay, I will write it as some normalization factor a by root of 2 pi h bar and whatever pi by beta whatever came. Is that okay? I'll take only functionality part. Okay, because normalization is not so big deal here. What is this one? E power minus beta by h bar into mod x. Am I right? So do you remember what is the normal? I mean, what is this one? This is in case of our Dirac function. Well, okay. Do you remember what is the normalization factor? That's the root of this one, as I remember. Okay, speak up. Root of beta by h bar e power minus beta by h bar into mod x. Okay, speak up. Check all calculation. Look at here. In this one, what is expectation x? Very simple. Why? Even function, isn't it? What is expectation x square? Expectation x square is very easy to find here. Okay, mod psi square beta by h bar integral minus infinity to plus infinity. What is this one? X square into e power minus 2 beta by h bar into mod x. Okay, you can write it as 2 times 0 to infinity x square into e power minus 2 beta by h bar mod x is x. Speak up. In the limit 0 to infinity. What is this one? 2 beta by h bar x power n into e power minus ax gamma of n plus 1 divided by a power n plus 1. What happened? What is gamma of 3? That is 2. 2 factorial. 2 factorial is 2. So 2 into h bar by 2 beta the whole square. Am I right? That is equal to, what is that? H bar by h bar square by 2 beta square. Fine. H bar square by 2 beta square. Okay. Now you need delta x, that's equal to root of expectation x square minus expectation x the whole square. Expectation x is 0. Okay. What is this one? H bar divided by root 2 into beta. Check this out. H bar divided by root 2 into beta. Fine. Can you do it again? In the momentum space, it is lengthy. What you need to do? You need to take the second derivative and all. Am I right? P cap square. Pick up. In the momentum space, okay? I mean, if you want to do this x square operator, okay, speak up. You need to sandwich that one, okay? Speak up. So just like here, isn't it? You need to sandwich. You need to take second derivative. Okay, then some term will come outside. Then you need to do that infinite integral. That infinite integral again it requires uh, some substitution. Okay, trigonometric substitution. So trigonometric, so tan theta substitution. Am I right? That's too lengthy. So now look at here. Once you transform back, okay, so that function is very easy to handle. Am I right? E power minus kappa mod x kind of thing. Okay, speak up. Now look at here. I have shown some confidence to write all of the constant as beta and then normalize it. While integral also something came, right? Pi by a or something. I just added, I just absorbed all of them to one constant beta. Anyway, later I'm going to find it using normalization. Functionality part is important for me. Even if you take some time and if you normalize, okay. I mean, I wrote this normalization constant directly by looking into this function because I remembered that what you call finite square well, I energy eigenstate, I energy eigenvalue. Do you remember? E power minus kappa mod x. This normalization constant was root kappa. Okay, that's how I quickly wrote that one. Okay, even if you spend some time in normalizing, it's better. Okay, speak up. But I mean, don't keep all of this lengthy part. Am I right? A by root of 2 pi h bar. I think pi by beta. Am I right? Isn't it? Then again, while normalizing, again you will end up with this one only. Is that okay? Speak up. If you all find this A, okay, using that normalization, again you will end up with that one only, that factor only. Okay. What I did, okay, I grabbed the functionality part. Rest of all, what you call, I took it as B, capital B, normalization constant. I found it using normalization. Okay, that is the basic idea. Okay, that saves some time. Okay, speak up.